Okay, last concept in our chapter. We're going to talk about some basic series RC circuits. What we mean by RC, we mean they have R, a resistor, and C, a capacitor. So we are going to look at two basic situations. The first one is called a charging circuit. We are going to assume initially there is no charge on the capacitor. So we have a battery that we're going to connect to a capacitor and a resistor in series. And the moment everything is connected, there is no charge on the capacitor. So if there's no charge on the capacitor initially, so delta V for a capacitor is equal to the charge that is on either plate divided by the capacitance. So the moment so T equals 0, meaning the moment the circuit is connected. The delta V for the capacitor is 0 because it started with no charge and it cannot instantaneously have a ton of charge. The resistor, though, its voltage depends upon how much current is flowing through it and its resistance. As soon as the circuit is closed, current will start to flow. If at this exact moment the circuit is closed, the capacitor has no voltage across it, then the battery voltage must be completely across the resistor. If we think about the loop rule, the battery putting in a certain voltage, then that voltage is shared somehow between the capacitor and resistor. This is true at all moments in time, but delta V for the capacitor and delta V for the resistor will change over time as time goes on. So again, the moment the circuit is connected, because we're assuming no charge on the capacitor initially, at that moment the capacitor has no voltage, which means the resistor has to have all the voltage of the battery. But as this current continues to flow, charges will start to accumulate on the capacitor. The side of the capacitor connected to the positive terminal of the battery will become positively charged, and the other plate will become negatively charged. So as time goes on, the delta V of the capacitor increases as Q increases. But if delta V is increasing, then delta V for the resistor has to be decreasing. The battery voltage is fixed. The voltage from the battery is a constant value. We're assuming it to be ideal. So the battery will provide the same potential difference the whole time. If delta V for the capacitor, though, is increasing, then delta V for the resistor has to decrease so that they always add up to be equal to that battery voltage. This is going to happen until delta V reaches a maximum value. After a long time. I'm putting long in parentheses because it's not really necessarily a long time. Like if we think of something taking a long time, we're thinking hours or days. A long time for a capacitor is still microseconds, milliseconds. It depends upon the value of the capacitor, resistor, and battery. After a long time, though, essentially what I mean by that, delta V for the capacitor reaches a max value, the biggest it can possibly get in this circuit. Well, the biggest it can possibly get is up to the battery voltage. So delta V for the capacitor is going to increase until it eventually reaches the battery voltage. Well, remember, the battery voltage has to add up to be the capacitor's voltage and resistor's voltage. If the capacitor has reached the battery voltage, then the resistor's voltage must be 0. Because if it wasn't, they would add up to be something different than the battery voltage. So essentially, after a long time, when the capacitor reaches its maximum voltage value, current stops. Right? For a resistor, delta V is I times R. It's not, the resistor value is not changing. So for delta V for the resistor to go to 0 means the current has to stop flowing. So ultimately, what we end up seeing, couple things. If we want to talk about the charge on the capacitor increases exponentially until it reaches a maximum value. The maximum value of charge occurs when the capacitor has its maximum voltage. So we can say Q max is the capacitance times the battery voltage. We can also draw a graph of potential difference versus time. The potential difference for the capacitor is going to mirror the charge equation. The resistor's voltage will decrease and reach 0. So ultimately, we know the delta V across the capacitor is Q over C. Since the charge is changing with time, the potential difference across the capacitor is changing with time. But because delta V for the capacitor plus delta V for the resistor have to add up to be the battery voltage, if delta V for the capacitor is changing with time, then delta V for the resistor also has to be changing with time. They always have to add up to be the battery voltage. What we end up with, now this is specific to what we're calling a charging circuit, because we're charging the capacitor up. We're starting with no charge and ending up with as much charge as possible, a maximum charge. Ultimately, we end up with a differential equation that you don't need to know how to solve because differential equations is not a prerequisite. Delta V for the capacitor is charge per capacitance. Delta V for the resistance is current times resistance. But remember, current is defined as the rate at which charge is flowing. So we end up with an equation that has both Q and dq dt in it. So we need a function that will satisfy this equation. The result looks like this. The charge on the capacitor as a function of time equals the maximum charge it can reach times 1 minus e to the negative t over rc. So as we've already mentioned, Q max is C, the capacitance, times the battery voltage. T here is whatever time we care about. It's just some moment in time we're calculating for or asked about. This quantity of R times C is called a time constant. We use the Greek letter tau to represent it. By the way, R in ohms times C in farads has units of seconds. This time constant is a specific amount of time. After one time constant, the charge is at 63% of its maximum value, if I remember right. All we're doing is putting in Q max 1 minus e to the negative RC over RC. If I take 1 minus e to the negative 1, I get 0.63 Q max. So it's just, this time constant is related to the amount of time it takes to reach 63% of its maximum value. The next time constant, it will have reached 63% of what's left to reach. The percentage is not necessarily all that specifically important. It's just keeping in mind that the larger the time constant, the longer it's going to take for this particular capacitor to charge. Okay, still may not be terribly long, but bigger time constant is more time needed to charge. So in this charging situation, we end up with the charge on the capacitor as a function of time. We could also write equations, for example, because the charge is changing with time, the potential difference across the capacitor is going to change with time. We could write that delta V across the capacitor as a function of time. I'm going to put in C times epsilon for Q max. And then we have to divide by C. This equation is back from when we talked about capacitors in general. So it's not written again in this section of the test notes, because we've already covered it. We've talked about capacitors. We can now take this new equation for charge and write an equation to represent the voltage across the capacitor as a function of time. Similarly, we could write an equation that describes the current as a function of time. We would just need to take the derivative of this charge equation. And then we could write an equation for the resistor, I times R. So the new part here is how this charge on the capacitor is accumulating with time. Capacitor does not charge instantaneously. It doesn't just instantaneously have a maximum amount of charge. Okay, so charging circuit. A charging circuit, we are specifically saying Q is 0 initially on the capacitor. A charging circuit is going to have a battery. That battery is going to cause current to flow when the circuit is connected, and that current flowing will charge the capacitor. The other situation we're going to talk about is called a discharging circuit. So charging means accumulating charge building up. Discharging means losing charge. So in this case, we have to say the capacitor, and that's not how you spell it, Trina. Capacitor initially, I'm glad I don't teach spelling or anything like that, has charge Q naught. So the capacitor has to have been connected to a battery for some period of time to start with this initial charge. But we disconnect the capacitor from the battery and we connect it across some sort of resistor. When the battery is no longer connected, there's nothing there to maintain the potential difference across the capacitor. The charges are not going to remain separated. And so these charges are going to start moving through the circuit, meaning we get some current, and they're going to start moving until equilibrium has been reached. So these charges move around, and by equilibrium, we mean we end up with a capacitor that has no net charge, and then also no current. So these charges flow quickly in terms of current to reach an equilibrium, a no potential difference situation. In this case, if we follow the loop rule, so let's say I start right here. If I go around my loop this way, I would see an increase in potential across my capacitor. But as I come over here, since I'm moving with the current flow, I'm going to see a decrease in potential across the resistor. The capacitor's voltage and the resistor's voltage end up having the same magnitude. They're just opposite in polarity. Okay, well, a capacitor, though, we know its potential difference is equal to Q over C. A resistor's potential difference is equal to IR. So those have to add up to be 0. But again, I is the rate at which charge flows, so it's dq dt. We end up with Q needing to be a function such that when we take the derivative of it, we can set up this equation and have them add up to be 0. The solution to that differential equation tells us that the charge on the capacitor plates as a function of time is equal to the initial charge that the capacitor has when this circuit is connected times the e to the negative t over RC. It's an exponential function. If we were to graph charge versus time, it would start at a Q naught value and decrease exponentially to 0. And it happens quickly. It's not something that takes very long, but it cannot happen instantaneously. So there is some sort of time frame required to discharge a capacitor. It's a very, very small time frame, most likely, but it is not instantaneous. This quantity of RC is still called a time constant. The ohms times the farad still gives us seconds. In this case, though, when if we plug in T is equal to tau, we get the charge at that time is 0.37 of that initial charge. So it's essentially just saying after one time constant has passed, we still have 37% of that initial charge left. So again, the time constant is essentially giving us an idea of, it's not completely discharged, but how fast discharging could potentially be. Okay, this equation is the new equation specifically for discharging. A discharging circuit, we have to start with an initial charge, but a discharging circuit has no battery connected anymore. It had to be connected at one point because that's how the capacitor would have become charged in the first place. But now the capacitor is connected in such a way that the battery is no longer connected. And that's why the charge moves around to bring the potential difference across the capacitor to 0. So capacitors, they store energy, remember, so this discharge is a way to get a quick flow of current. So like the cardiac defibrillators, if you've ever watched TV shows, charging, and they're holding the paddles, they're charging those paddles up to be a capacitor. And when they press the button on the person's chest, they're discharging that capacitor. They're getting that charge to flow through the person's chest quickly. And the hope is that that current flow, since our hearts operate on electrical currents, they're hoping that this quick current flow will disrupt what the heart is doing currently and that it will restart normally again. Now, it's not used in every situation or anything, and of course this is not a medical class, but just the idea behind it. That's a good example of a discharging circuit.